From somewhere beneath your feet, past the bedrock and the soil and the ancient stone, there are places on this earth that have never once seen light. Not in 1,000,000 years, not in 10 million. From sealed beneath kilometers of moving, grinding, crushing ice, hidden from every instrument we've ever built, there are worlds we know exist but cannot reach. Worlds that may hold water older than our species, ecosystems that evolved in total darkness, and answers to questions we haven't even learned to ask yet. We have sent machines to the surface of Mars. We have photographed galaxy billions of light years away, and yet just a few kilometers beneath the glaciers of the North Pole, there is a realm so hostile, so unyielding, that all of our technology has barely scratched its surface. This is the story of why. To understand why that statement is so startling, you have to understand what we mean when we say we cannot reach something. We are not talking about a lack of interest. Polar science has attracted some of the most determined minds on Earth for more than a century. We are not talking about a shortage of funding, though funding is always limited. We are talking about something more fundamental, a set of physical conditions so extremes, so layered, and so dynamic that they defeat our best tools before those tools can finish the job. The world beneath the North Pole's glaciers is not simply cold and dark. It is a place governed by rules that work against exploration simultaneously. Pressure that crushes equipment. Ice that flows like a slow river and closes over anything inserted into it. Water that behaves differently under immense weight than it does at the surface. And a total absence of communication because nothing we transmit, no radio signal, no wireless data stream, passes cleanly through kilometers of glacial ice. This documentary is about why that combination has proven so difficult to crack and what it means that we are still trying. The story begins not with a single expedition or a single discovery, but with a shape. The shape of the Arctic itself. Most people, when they picture the North Pole, imagine a fixed point of frozen land, something you could stand on and photograph. In reality, the geographic North Pole sits in the middle of the Arctic Ocean, a body of water roughly 14 million square kilometers in area, covered year-round by floating sea ice. There is no land beneath your feet at the pole itself. There is ocean, sometimes more than 4,000 meters deep, capped by ice that drifts and shifts with the wind and the current. That distinction matters enormously because it means the Arctic is not a single kind of environment. It is a layered system. Floating sea ice on top, rugged seafloor below that, and surrounding it all on three sides the great landmasses of North America, Europe, and Asia, each draped in their own glaciers and ice caps that spill toward the sea. The largest of those glaciers is the Greenland ice sheets, which sits to the side of the pole but dominates the regional geography. It covers roughly 1.7 million square kilometers, and in its thickest sections it rises more than 3 kilometers above the bedrock. It is not a static object. It flows very slowly by any human measure, but unmistakably outward from its center toward its edges, where it calves icebergs into the surrounding ocean. Scientists have known this for generations. What took far longer to understand was what was happening at the bottom of that ice, at the interface between glacier and bedrock, in the zone that no one had ever seen. The earliest serious attempts to understand what lay beneath the ice came not from explorers descending into the ice, but from physicists and geologists working at the surface, or rather from the signals they sent downward. In the middle of the 20th century, researchers began using radio echo sounding, a technique that works on the same principle as radar. A pulse of radio energy is sent into the ice, and the time it takes to bounce back from different layers reveals the ice thickness and the shape of what lies below. The results were astonishing. The bedrock beneath the Greenland ice sheet was not flat, it was deeply carved. Valleys that would be Grand Canyons if exposed to open air ran for hundreds of kilometers beneath the ice. Basins sat hundreds of meters below sea level, scoured by the glacier over millions of years. And in places where the radar signal showed anomalous reflections, the kind of flat, bright return associated with liquid water rather than solid rock or sediment, there were hints of something that should not have been possible under that much frozen weight. Water. Liquid water sealed away and sitting quietly in the dark. Those early radar surveys were imprecise by modern standards, and the scientists conducting them were cautious in their conclusions. But the signal was there. Beneath hundreds of meters of solid glacial ice in a place where the temperature was many degrees below freezing at the surface, something was reflecting radar energy the way a still lake reflects a beam of light. The explanation, when it came, was elegant and counterintuitive. From pressure changes the melting point of ice. Under enough weight, ice will melt at temperatures well below 0 degrees Celsius. At the base of a glacier 3 kilometers thick, the pressure is roughly 300 times greater than atmospheric pressure at sea level. From that pressure depresses the melting point low enough that geothermal heat rising slowly from Earth's interior, combined with the frictional heat generated by the ice grinding over bedrock, is sufficient to melt the bottommost layer, not dramatically, not in a gush, but steadily, persistently, across vast areas, creating thin films and pooling in depressions, creating lakes that had no business existing in one of the coldest places on Earth. This realization shaped how scientists thought about glaciers. They were not simply frozen obstacles, they were hydrological systems. Complex, layered, and active. Water formed at the base, moved through channels and cavities carved by its own pressure, pooled in subglacial basins, and eventually found its way to the ocean, sometimes quickly through drainage events, sometimes not for thousands of years. The glacier was, in a sense, managing its own plumbing system entirely beyond human view. The question that followed was obvious, and it carried an urgency that went beyond academic curiosity. If liquid water could persist beneath kilometers of ice, sealed away from sunlight, and insulated from almost everything that happens at the surface, then what, if anything, was living in it? Life requires energy. It requires some chemical transaction, some way of extracting order from disorder. On the surface, that transaction is almost always powered by sunlight, at least at the base of the food chain. But in the 1970s, ocean floor exploration revealed that sunlight was not the only option. Hydrothermal vents on the deep sea floor, fueled entirely by chemical reactions between hot mineral-rich water and the surrounding ocean. No photosynthesis, no sun, just chemistry and pressure and time. Microbes oxidizing hydrogen sulfide and producing organic matter that fed tube worms, crabs, and shrimp in the perpetual dark. If life could do that at the bottom of the ocean, it was at least theoretically possible that life could do something similar beneath a glacier. Not the same organisms. Not the same chemistry, necessarily, but the same basic principle. Energy from rock, energy from the slow decay of minerals, energy from the friction of ice against stone. Enough, perhaps, to sustain microbial communities that had been isolated from the surface world for a very long time. Possibly a very, very long time. Scientists who study extremophiles, organisms that thrive in conditions most life cannot tolerate, began to take this possibility seriously in the 1980s and 90s. They found microbes in boiling hot springs. They found them inside Antarctic rock, surviving on trace amounts of moisture and light. They found them in the permafrost of Siberia, alive after tens of thousands of years of freezing. Each discovery pushed the boundary of what was considered habitable. And each discovery made the question of what lay beneath the Arctic ice feel less like speculation and more like something that required a direct answer. But here is where the story begins to complicate itself. Because the environments that might support life beneath the ice are precisely the environments that are hardest to reach without destroying them. A subglacial lake sealed for 100,000 years is pristine. It has had no contact with the modern atmosphere, no exposure to the organisms that blanket every surface on Earth. The moment you drill into it, you risk introducing microbes from the drill, from the drilling fluid, from the air, from the hands of the person who assembled the equipment. You risk contaminating the very thing you traveled thousands of kilometers across ice to study. And if you contaminate it, the contamination cannot be undone. The lake does not reset. The ecosystem, if it was there, may be overwhelmed before a single sample can be analyzed. This was not a theoretical concern. It was a practical one that shaped every major polar drilling project of the late 20th century. In Antarctica, at a place called Lake Vostok, Russian scientists had been drilling downward since the 1970s, chasing a massive subglacial lake buried beneath nearly 4 kilometers of ice. The lake was enormous, larger than Lake Ontario. It had been sealed away for at least 15 million years. When the drill finally approached the water surface in the 1990s, it stopped. not because of a mechanical failure, but because of a scientific argument. From the international community was not convinced that the equipment was clean enough. The drilling fluid used to keep the borehole from collapsing was a mixture of kerosene and freon. Not exactly what you want dripping into a pristine ancient lake in the hope of detecting delicate life. The project was paused, debated, redesigned, and ultimately the lake was finally reached in 2012, decades after the drill first began its descent. And even then, the samples recovered from the borehole were ambiguous. Contamination could not be fully ruled out. The question of whether anything lived in that lake remained open, which meant the question of what might live beneath the Arctic remained open too. The tools existed to drill downward. The will existed to ask the question. What did not yet exist was a method clean enough, precise enough, and robust enough to answer it without risking the destruction of the very answer being sought. So the problem was not simply getting through the ice. It was getting through without leaving a trace of yourself behind. And that constraint, more than any engineering limitation, shaped the entire next chapter of polar exploration. It forced scientists to think differently about what a drilling system needed to do. It was not enough to descend. The descent had to be clean, sterile, controlled in a way that no industrial drilling operation had ever been required to be, because no industrial drilling operation had ever cared what it was drilling into. The engineering response to this problem unfolded slowly across several research programs running in parallel on opposite ends of the Earth. In Antarctica, American, British, and later international teams began developing what they called clean access protocols. Every component of a drill system that would contact the ice or the water below had to be decontaminated before deployment. The drilling fluids that kept boreholes from collapsing had to be replaced with something less chemically aggressive, something that would not poison whatever it touched. Researchers experimented with silicone oils, with filtered water held under pressure, with systems that avoided drilling fluid entirely by using heated water jets to melt a path downward rather than cutting through the ice mechanically. Each approach came with its own trade-offs. Hot water drills were fast, but they required enormous amounts of energy, and the boreholes they created began refreezing almost immediately. A window of hours, sometimes less, was all that was available to lower instruments through the hole and retrieve samples before the shaft closed. Mechanical drills were slower but produced more stable boreholes. The problem was the fluid, always the fluid. While the Antarctic programs wrestled with these questions, a parallel effort was taking shape in the Arctic. The Greenland ice sheet, though less studied than its southern counterpart in the 1980s, was beginning to attract serious scientific attention for a different reason: climate. The Greenland ice core record, drawn from boreholes that sampled the layered history of snowfall reaching back hundreds of thousands of years, had revealed something alarming. Earth's climate had not changed gradually or smoothly over the past ice ages. It had lurched. Temperatures had shifted by 10 or even 15 degrees Celsius in the span of decades, not millennia. The ice held evidence of violent, rapid transitions between cold and warm states, transitions that had happened before humans existed, and that could, in principle, happen again. Unlocking more of that record required drilling deeper, and drilling deeper meant confronting, again, the question of what happened when you reached the bottom. The deeper the borehole, the closer you came to the basal melt layer. The closer to the melt layer, the greater the risk of breaching it. Scientists began mapping Greenland's subglacial topography with increasing precision, using improved radar systems mounted on aircraft that could fly survey grids over the ice sheet and build three-dimensional pictures of the bedrock below. What those surveys revealed was that Greenland's hidden landscape was even more complex than the early work had suggested. There were not just a few isolated valleys. There was an entire system of interlocking basins and channels, many of them sitting hundreds of meters below sea level, carved over millions of years of glacial erosion. Some of these basins were almost certainly holding water. The radar signatures were unmistakable to trained eyes. Flat, bright specular reflections at the icebed interface, the signature of a liquid surface, not rock or sediment. The question shifted from whether the water was there to how much of it existed, how it was connected, and how it moved. And the answer, as it emerged through the 1990s and into the early 2000s, was that it moved in ways that were far more dynamic than anyone had anticipated. Satellite measurements of the ice surface began showing something strange. In certain regions of Greenland, the surface of the ice sheet rose and fell by small but measurable amounts over periods of weeks or months, independent of any change in snowfall or melt. The only explanation that fit the data was that large volumes of water were moving beneath the ice. Subglacial lakes were filling and draining through channels, and as they did, the ice above them rose and sank like a slow, vast lid. The same phenomenon had been observed in Antarctica, where over 400 subglacial lakes had been identified by that point. But in Greenland, the drainage events appeared to be more frequent and more directly connected to changes happening at the surface. When summer meltwater poured down through crevasses and vertical shafts in the ice, it reached the bed and flooded the subglacial drainages, temporarily raising water pressure and accelerating the glacier's slide over the bedrock. The glacier was not isolated from the atmosphere above it. It was coupled to it, responding to surface conditions through a plumbing system that was invisible, unmapped, and almost entirely uncontrolled. That coupling was the first major turning point in how scientists understood the Arctic's hidden world. Because it meant that the subglacial environment was not just a curiosity sitting passively beneath the ice. It was a mechanism, a working part of the glacier's dynamics that influenced how fast the ice moved, how quickly it delivered mass to the ocean, and therefore how much it contributed to rising sea levels. The question of what lay beneath the ice suddenly had direct urgent relevance to the world above it. If researchers could not understand the subglacial drainage system, they could not accurately predict how the Greenland ice sheet would respond to a warming climate. And if they could not predict that, their sea level projections had a gaping hole at their center. Funding for subglacial research increased. International collaborations formed. New radar systems were designed specifically to image basal water with higher resolution. Seismic surveys were run across the ice sheet, using the echoes of sound waves to probe structures that radar could not fully resolve. The picture that emerged was not simpler than the one that preceded it. It was far more complicated. The drainage beneath the Greenland ice sheet was not a single organized network of channels like a river system scaled up to continental proportions. It was a shifting, patchy mosaic of drainage styles that changed from season to season and region to region. In some areas, meltwater moved through efficient, channelized pathways that could drain large volumes quickly. In others, it spread in thin, distributed films across the ice-bed interface, maintaining high water pressure over wide areas and keeping the ice lubricated across entire sectors of the glacier. The boundary between these drainage regimes moved. It responded to changes in meltwater input, to shifts in ice thickness, to the seasonal rhythm of surface warming and refreezing. Mapping it at one moment did not guarantee that the map would still be accurate 6 months later. This was the landscape that any exploration mission would have to enter. Not a static cave system that could be charted once and then navigated reliably. A continuously reconfiguring environment in which the terrain itself was a moving target. And the instruments that would need to function in this environment were not simple. They were among the most technically demanding devices ever built, designed to withstand pressures that would crush a standard submarine hull, to operate in near-total darkness without any possibility of real-time communication with the surface, and to do all of this without introducing a single living cell that did not already belong there. The gap between what was required and what was available was not small. It was not a gap that clever engineering could bridge in a single funding cycle. Researchers who understood the problem clearly said so, publicly and in print. The tools that existed in the early 2000s could get you close. They could drill to within meters of a subglacial lake. They could detect its presence with high confidence. What they could not do was enter it cleanly, operate within it reliably, and return data of sufficient quality to answer the questions that justified the mission. The environment demanded instruments that did not yet exist, and building those instruments required knowing in detail what conditions they would face. Which meant entering the environment, which required the instruments. The circularity was not lost on anyone involved. And then, in the middle of this frustrating impasse, something changed. Not a breakthrough in drilling technology, not a new radar system or a more powerful satellite. What changed was the discovery that the barrier was being breached from below, in Antarctica, in a place called Lake Willans, where a team of American researchers had spent years designing a hot water drill system clean enough to meet international planetary protection standards. When they finally punched through in January of 2013 and lowered their instruments into water that had been sealed beneath the ice for potentially millions of years, they found something that immediately reframed everything. They found life. Not traces of life, not ambiguous chemical signals. Active, metabolizing microbial communities living in waters so cold and so dark and so remote from anything we would consider hospitable that their very existence demanded a new answer to an old question. And that answer, when it settled into the scientific community over the months that followed, sent a very clear signal northward. If life was there, in Antarctica, beneath nearly a kilometer of ice, in a lake that had been cut off from sunlight since before modern humans walked the Earth, then the question of whether life existed beneath the Greenland ice sheet was no longer theoretical. It was a matter of going to look. The Lake Willans discovery did not travel quietly through the scientific community. It arrived like a stone dropped into still water, and the ripples moved outward in every direction at once. Here was proof, not inference, not model output, not a hopeful extrapolation from indirect data, but direct physical evidence that microbial life could persist in a subglacial lake buried beneath Antarctic ice. The organisms detected in the water samples were not fossils. They were not remnants of ancient biology preserved in amber-like conditions. They were alive, they were metabolizing, they were cycling carbon and nitrogen and sulfur through pathways that required no sunlight, no atmosphere, no connection to the world above. They were doing what life does, quietly, persistently in the dark. The immediate scientific response was cautious, as it should have been. Contamination remained a concern. The team that executed the Lake Willans project had designed their hot water drill to meet rigorous cleanliness standards, filtering the meltwater used to bore the hole and sterilizing equipment with ultraviolet light and hydrogen peroxide. But rigorous is not the same as perfect. Some researchers questioned whether the microbial signal in the samples was entirely indigenous or whether surface organisms had found a way in despite precautions. The debate was professional, not hostile, and it was exactly the kind of scrutiny that good science requires. What it could not do, however, was undo the core finding. Life had been detected. The methodological arguments were about signal strength and confidence intervals, not about whether the signal existed at all. And that changed what it meant to look northward. Because Lake Willans sat beneath roughly 800 meters of ice, not 3 kilometers, not the full depth of the Greenland ice sheet's thickest sections. 800 meters, less than a third of the depth that separated the surface from the base of Greenland's deepest glacial troughs. If life could establish itself at that depth in Antarctica in a lake sealed away from surface conditions, then the question for Greenland was not whether life could theoretically exist there. The question was what kind of life, sustained by what energy sources, and isolated for how long. Researchers already had pieces of the answer. Meltwater emerging at the edges of the Greenland ice sheet, where glaciers calve into fjords or drain across outwash plains, had been sampled for years. Those samples contained microbial communities. The organisms were diverse and active. Some were metabolizing sulfur compounds derived from the weathering of bedrock minerals. Others were fixing nitrogen, drawing energy from reactions between iron-bearing rocks and water. The chemical signatures in the outflow water, elevated concentrations of dissolved minerals, organic carbon, and gases like methane and hydrogen, all pointed to active biological and geological processes occurring somewhere beneath the ice, processes that the water carried with it as it finally escaped into the open air. But outflow samples were indirect. They were the end product of a journey that might have taken the water through dozens of kilometers of subglacial channels and cavities before it ever reached a sampling bottle. The communities detected in that water might not reflect what was happening deep beneath the ice. They might be organisms that colonized the drainage system near its outlet, far from the sealed basins where the most ancient and isolated communities, if they existed, would be found. To understand what was actually living in Greenland's subglacial environment, you would need to go there. and going there meant solving problems that the Lake Whillans project, successful as it was, had not fully resolved. The first problem was depth. 800 meters of Antarctic ice had taken the Whillans team's hot water drill roughly 30 hours to penetrate. From 3 kilometers of Greenland ice under far more logistically challenging conditions would take dramatically longer. From the borehole would need to stay open while instruments were deployed, and ice under higher pressure and colder mean temperatures would refreeze faster and more aggressively than the relatively warm basal ice at Whillans. From the energy required to maintain the hole would be immense, and every additional hour of operation increased the risk of equipment failure, drilling fluid contamination, or borehole collapse. The second problem was location. From Lake Whillans had been chosen partly because it was accessible by land-based logistics, reachable by the overland traverse vehicles that supply research stations in West Antarctica. From the subglacial lakes and basins beneath the Greenland ice sheet are distributed across an interior that is logistically harder to reach in some respects and politically more complicated in others. From Greenland is an autonomous territory within the Kingdom of Denmark, and large-scale drilling operations require coordination with Danish and Greenlandic authorities, environmental review, and in some cases negotiation over what happens if something goes wrong. From these are not insurmountable obstacles, but they add layers of preparation time and institutional complexity that purely scientific programs sometimes struggle to navigate. The third problem was the target itself. The subglacial water bodies beneath Greenland were not as well characterized as the Antarctic lakes. From scientists knew they existed. The radar surveys and satellite elevation data were clear on that point. But the detailed geometry of those water bodies, their depth, their volume, their connectivity to the larger drainage system, their chemical environment remained poorly resolved. From drilling into a subglacial feature without knowing its exact dimensions and behavior was like navigating into an unmapped cave with a light that reached only a few meters. You might find what you were looking for. You might find something completely different. From and the consequences of misjudging the target, breaching a pressurized cavity unexpectedly, for example, could be costly both for the equipment and for the integrity of any samples collected. This is where the next chapter of the story becomes both more specific and more sobering. From because in the years following the Whillans discovery, multiple research groups began designing Greenland-focused subglacial access projects, and each of them ran directly into the same set of compounding obstacles that had frustrated every previous attempt. From one such effort centered on a region of the ice sheet where satellite data had detected repeated cycles of surface subsidence and uplift, the telltale signature of a subglacial lake draining and refilling. The feature was real, its behavior was documented, the scientific case for targeting it was strong. But when researchers began planning the access mission, they encountered the full weight of what it actually meant to operate a sterile deep ice drilling system in the field. The infrastructure requirements alone were staggering. From a hot water drill capable of reaching basal depths beneath the Greenland ice sheet would need to melt and pump thousands of liters of water per hour, filtering and sterilizing that water continuously to maintain cleanliness standards. From the heating equipment, pumps, filters, ultraviolet sterilization units, and associated generators would need to be transported to a site that was accessible only by aircraft or overland vehicles traveling across hundreds of kilometers of bare ice. From every kilogram of fuel, every spare part, every instrument casing had to be flown in, and the cost per kilogram of anything transported to a remote high-altitude ice sheet site is not trivial. From the logistical budget for a single deep access mission could approach or exceed the annual research budget of an entire polar science department. Then there was the time constraint. The drilling window at a Greenland interior site might be limited to a few weeks of reasonably stable summer weather. Setup took time. From testing the system before committing it to a deep bore took time, and if something failed partway through, there might not be enough time remaining in the season to fix it and try again. From teams that had spent years designing and funding a mission could find themselves flying home with a borehole that closed before the instruments ever reached the water. These were not hypothetical frustrations. They were documented realities that had shaped the trajectory of subglacial research for decades. and they illuminated something that went beyond any particular equipment failure or budget shortfall. The problem was systemic. The environment demanded a level of engineering sophistication, logistical capacity, and operational patience that could not be assembled quickly or cheaply, and that was extraordinarily difficult to test under realistic conditions before committing to a full mission. You could test a hot water drill in a temperate glacier. You could test sterilization protocols in a laboratory. What you could not easily test was the complete integrated system. Drill plus instruments plus sampling devices plus communication links plus contamination controls, operating simultaneously at depth, under pressure, in a remote location with no support infrastructure and a closing window of available time. The gap between what the science demanded and what the engineering could reliably deliver was not a gap that enthusiasm could close. It required a different kind of investment. Not just more money poured into the same approaches, but a fundamental rethinking of how exploration systems for icy environments were designed from the ground up. And that rethinking was beginning to happen, slowly, in laboratories and engineering workshops far from the ice. Researchers working on planetary exploration, specifically the challenge of one day reaching the subsurface oceans of Europa or Enceladus, had arrived at the same design problems from a different direction. They too needed systems that could melt or drill through thick ice, operate without human intervention in a sealed environment, avoid contaminating what they found, and transmit data back through a medium that blocked radio waves. The convergence of planetary science and glaciology around these shared engineering challenges was not accidental. It was increasingly recognized as an opportunity. If the same cryobot technology being designed for Europa could be adapted for Greenland's subglacial lakes, both programs would benefit. If the autonomous navigation systems being developed for ice-covered ocean exploration could be validated beneath an Antarctic ice shelf, they would arrive at Europa better tested than any previous space instrument. But this convergence also revealed something uncomfortable. The timeline for solving these engineering problems was not years, it was decades. The most optimistic projections for a functional cryobot capable of penetrating kilometers of ice cleanly and autonomously placed that milestone well into the future, even with sustained investment. And the Arctic was not waiting. The ice was changing. The climate was warming. The window for studying these environments in their current state before accelerating melt altered their chemistry, their structure, and possibly their biology was not indefinitely open. Which meant that while the long-term engineering programs worked toward future capability, researchers also needed to extract as much information as possible from the approaches that already existed, however imperfect, and one of the most productive of those approaches was not drilling at all. It was listening. Seismology had been used to study the Earth's interior for more than a century. The principle was simple enough. Sound waves travel through different materials at different speeds and reflect off boundaries between them. By generating a controlled vibration at the surface and recording how the echoes turn, scientists could infer the structure of what lay beneath without ever touching it. Applied to glaciology, seismic surveys offered something that radar alone could not always provide. They could distinguish between rock, sediment, ice, and water with a precision that depended on the quality of the equipment and the skill of interpretation, but that in favorable conditions was remarkable. Where radar saw a bright flat reflection and said water is probably here, seismic data could say more. It could suggest whether the water sat in a thin film or a deeper body. It could hint at the nature of the sediment below. It could identify zones of deformation within the ice that revealed how the glacier was moving and where its internal stresses were concentrated. Teams working in both Greenland and Antarctica expanded their seismic survey programs through the 2000s and into the 2010s, deploying arrays of sensors across the ice surface and recording not just deliberate vibrations but the natural seismicity of the glaciers themselves. And that is where listening became genuinely revelatory. Because glaciers, it turned out, were extraordinarily noisy. They cracked and groaned. They produced swarms of small earthquakes as the ice fractured under stress. They generated low-frequency tremors that propagated for hundreds of kilometers through the ice sheet, signals that had no obvious source at the surface but originated somewhere in the basal zone, where ice met water met rock in a zone of perpetual mechanical negotiation. From these signals, called glacial earthquakes or icequakes, had been known for years. What changed was the understanding of what they meant. From research published in the mid-2000s showed that the largest glacial earthquakes in Greenland, events comparable in seismic magnitude to moderate tectonic earthquakes, were not random. They clustered in time. They peaked in summer and early autumn, coinciding almost exactly with the period of maximum surface melt. That timing was not a coincidence. It reflected the connection that had already been suspected from satellite data. Surface meltwater was descending to the bed, flooding the basal drainage system, raising water pressure and lubricating the ice-bed interface. The glacier would then lurch forward in sudden accelerations, and those lurches generated seismic signals that propagated outward through the ice and the crust beneath. By listening to those signals carefully enough, scientists could track what the drainage system was doing without ever entering it. The seismic record also revealed something that complicated the picture in an important way. The relationship between surface melt and basal lubrication was not linear. In the early part of the melt season, when meltwater first began reaching the bed in significant quantities, glacier velocity spiked. The ice accelerated sharply as water pressure rose and friction dropped. But as the season progressed and meltwater continued to flood the subglacial system, the velocity response changed. In some areas, the glacier actually slowed down later in the season, even as surface melt remained high. The drainage system was adapting. As large volumes of water moved through the bed repeatedly, the inefficient distributed drainage network of thin films and linked cavities was being reorganized into a more efficient channelized system, one where water moved quickly through discrete conduits rather than spreading as a pressurized sheet across the ice-bed interface. Efficient drainage meant lower sustained water pressure, which meant more friction, which meant slower ice. This finding had profound implications. It meant that a warming climate, by delivering more meltwater to the glacier bed, would not necessarily cause a simple and continuous acceleration of ice flow. The response would be more complex, more nuanced. In some regions and some seasons, more meltwater might actually slow the glacier once the drainage system reorganized around it. In others, where the subglacial topography or the basal materials prevented efficient channelization, the water pressure would remain high and the acceleration would persist. Predicting which outcome would occur in which location required detailed knowledge of the subglacial environment that did not yet exist at the spatial resolution the models demanded. So the listening approach was enormously valuable, and it was moving the field forward. But it was also clarifying with increasing precision exactly what it could not tell you. Seismic data could reveal the mechanical behavior of the glacier. It could track the timing and pattern of basal water pressure changes. It could identify zones where drainage was channelized versus distributed. What it could not tell you was what the water chemistry was like, what minerals the meltwater was dissolving from the bedrock, what gases were dissolved in it, whether anything was growing in it. For those questions, you needed samples. And for samples, you needed access. And access remained the central unsolved problem. The urgency of that problem was sharpening for a reason that went beyond scientific curiosity. By the early 2010s, the rate of mass loss from the Greenland ice sheet had become one of the most closely watched numbers in climate science. Satellite gravity measurements from the GRACE mission, which tracked tiny variations in Earth's gravitational field caused by shifting masses of ice and water, showed that Greenland was losing ice at an accelerating pace. The numbers climbed from roughly 100 billion tons per year in the early 2000s to more than 250 billion tons per year by the 2010s. Each year seemed to revise the estimate upward. And within that broad signal of accelerating loss, the contribution from dynamic processes, meaning the acceleration and thinning of outlet glaciers rather than simple surface melt, was significant and poorly constrained. Poorly constrained because it depended on the behavior of the subglacial drainage system. The same system that no one had directly sampled, the same system whose geometry was known only in outline, the same system that was reorganizing itself in response to increasing meltwater inputs in ways that existing models could not reliably predict. From the connection between what happened at the glacier bed and what happened to global sea levels was not abstract, it was direct and measurable, and the gap in understanding the bed was now a gap in the ability to forecast how much the oceans would rise and how fast. From that's subglacial access not merely a scientific priority but a practical one. Governments planning coastal infrastructure needed projections. Insurance markets needed risk assessments. The answers to those questions were, at least in part, buried beneath kilometers of moving ice. From this pressure from outside the scientific community, from policymakers, from planners, from the climate modeling centers that fed their outputs into international assessments, created a new kind of institutional urgency around subglacial research. From funding bodies that had previously viewed deep ice drilling as an academic curiosity began to see it as applied science with tangible consequences. Programs that had operated on small budgets and long timelines began attracting attention from agencies that wanted results on shorter schedules. From the culture of polar fieldwork, which had always been defined by patience, by the acceptance of repeated failures and incremental progress, found itself being pushed to deliver faster and on terms that the environment itself did not accommodate. That tension produced a productive kind of friction in some cases. From it forced researchers to be more rigorous about what they could actually deliver versus what they hoped to deliver. It pushed engineering teams to prioritize the components of their systems that posed the highest risk of failure. From it encouraged collaboration across groups that had previously worked independently, sharing data and lessons learned rather than competing for priority over findings. But it also created pressure to attempt missions before the systems were fully ready, to interpret ambiguous results more confidently than the evidence warranted, and to make promises about timelines that the Arctic's physics would not honor. The ice did not negotiate. It did not care about funding cycles or policy deadlines. It moved according to gravity and temperature and the slow accumulation of millions of winters. And every time a research program underestimated that indifference, it paid for the mistake in lost equipment, closed boreholes, and seasons that ended without reaching their targets. One of the clearest examples of this dynamic involved the development of autonomous underwater vehicles for under-ice exploration. The concept was compelling and the engineering was genuinely advancing. Small robotic submarines capable of navigating beneath ice shelves, mask-CC ice-ocean interface, and collecting water samples had been deployed successfully in Antarctica, where they revealed the complex sculpted geometry of ice shelf bases being carved by warm ocean water. The images and data they returned were scientifically invaluable and visually striking, the kind of concrete discovery that justified continued investment. But translating that capability to the subglacial environment beneath a grounded ice sheet was a fundamentally different challenge. Ice shelves floated on open water. The space beneath them was accessible, at least in principle, by vehicles that could enter from the ocean edge. Subglacial lakes and channels beneath grounded ice were accessible only through the ice above them, which meant through a borehole. And boreholes, as every team that had drilled one knew, were temporary. They refroze, they narrowed under the pressure of the surrounding ice. The window of access they provided was measured in hours to days, not in the weeks or months that an autonomous vehicle mission might require to complete a meaningful survey of a subglacial basin. Researchers began exploring whether vehicles could be designed to deploy rapidly enough to take advantage of a hot water drill borehole, descend into the subglacial water, conduct their survey, and return to the borehole before it closed. The idea was elegant in principle. In practice, it required the vehicle to navigate in an environment it had never been tested in, find its way back to an opening that might have shifted or partially refrozen, and do all of this without any communication with the surface team because radio signals could not pass through the ice above it. If the vehicle missed the borehole on its return, it would be trapped. Not damaged necessarily, but irretrievably isolated, its data locked inside its memory, inaccessible. The cost of that outcome, financially and scientifically, would be severe. And this was the shape of the problem as it stood at the edge of the next decade. Not a single obstacle, but a nested sequence of them, each one conditional on solving the one before. To get a vehicle into the water, you needed a borehole. To keep the borehole open long enough, you needed more power and better insulation than current systems provided. To navigate the vehicle reliably, you needed maps of the environment it would enter. To get those maps, you needed the vehicle to go there first. Every solution pointed back to an upstream problem that had not yet been solved. The system demanded progress on all fronts simultaneously, but resources and time moved in only one direction, and the ice kept moving too, reshaping the target beneath every plan that was still being written. The assumption underlying almost every subglacial exploration program up to that point was a reasonable one. It went something like this. The subglacial environment was difficult to access, but it was stable enough that a well-planned mission could characterize it, sample it, and return useful data. The environment was hostile, yes, the engineering challenges were severe, but the target, however hard to reach, was there. It was waiting. Once the tools existed to reach it cleanly, the environment would yield its information. That assumption was not wrong exactly. But it was incomplete in a way that took years to fully appreciate, and when the implications became clear, they restructured the entire problem. What changed the picture was not a single dramatic discovery, but the gradual accumulation of data from a source that had not originally been designed for subglacial research. The ISAT satellite, launched by NASA in 2003, carried a laser altimeter that measured the elevation of the ice surface with extraordinary precision, accurate to a few centimeters across distances of kilometers. Its purpose was to track changes in the volume of the polar ice sheets over time, to monitor whether they were growing or shrinking. It was very good at that, but because it measured surface elevation continuously across repeated passes, it also recorded something that no one had specifically planned to capture. The ice surface was moving in ways that had nothing to do with snowfall or melt. It was rising and falling in specific locations, sometimes by a meter or more, on timescales of months. And the pattern of those movements, when researchers began mapping them systematically, revealed a subglacial drainage system that was not merely dynamic, it was violently so. The analysis, published in 2006, identified dozens of active subglacial lakes beneath the Antarctic's ice sheet, identified not by radar or seismics but purely by the signature of their filling and draining imprinted on the ice surface above them. Water was moving from one lake to another through connecting channels, traveling hundreds of kilometers beneath the ice. A lake would fill slowly for months or years, its surface ice rising as the water volume below increased, and then drain suddenly, sending billions of liters rushing through the subglacial network to the next basin downstream, which would then show its own surface rise as it received the flood. The process was not random, it was patterned. It formed cascades, chains of connected drainage events that propagated through the ice like pulses through a slow, frozen circulatory system. The immediate implication for exploration was stark. The subglacial lakes that researchers had identified as targets for drilling were not static ponds sitting quietly in the dark. They were nodes in an active, connected, constantly moving system. A lake that had been mapped by radar and selected as a target might drain completely in the months between the survey and the drilling mission. The feature being aimed at might not exist in the same form, or at all, by the time the drill arrived, and a lake that drained would not simply leave an empty basin. It would leave a chaotic residue of disturbed sediments, collapsed ice, and rerouted channels, a geological mess that might be scientifically interesting in its own right, but that bore little resemblance to the pristine sealed environment the mission had been designed to sample. This realization required a fundamental rethinking of how subglacial lakes should be categorized and targeted. Not all lakes behaved the same way. Some appeared in the satellite data to be stable over the full duration of the observation record, showing no significant surface motion above them. Others were clearly active, draining and refilling on cycles of years to decades. The distinction mattered enormously for mission planning. A stable lake, if such a thing truly existed and was not merely a lake that had not yet been observed draining, would be the preferred target for a contamination-sensitive biological or geochemical investigation. An active lake would be harder to hit reliably, but might offer different scientific value, a window into the dynamics of subglacial floods and the transport of materials through the drainage network. The problem was that the satellite record was short. ISAT operated until 2009, when technical failures ended its mission. Its successor, ISAT-2, launched in 2018, eventually extended the record. But even with both missions combined, the observation window for most subglacial features covered only a decade or two. That was enough to confirm that drainage events happened and to characterize their rough frequency in some regions. It was not enough to determine whether a lake that appeared stable in that window was genuinely stable on longer timescales, or simply in a quiet phase of a longer cycle. The ice sheet's memory extended back tens of thousands of years. The satellite record covered a blink of geological time. Conclusions drawn from it had to be held cautiously. But here was the pivot that changed everything, because the satellite data did not just reveal that subglacial lakes were unstable. It revealed that the drainage events were connected to something happening far above, at the surface of the ice in real time. When researchers cross-referenced the timing of lake drainage events with records of surface melt intensity, they found a correlation that was too consistent to be coincidental. Major drainage events beneath the ice sheet clustered in the aftermath of periods of intense surface melt. The water descending through the ice was not just lubricating the bed. In some cases, it was pressurizing the subglacial drainage network beyond its capacity to maintain existing lake boundaries, triggering sudden drainages that cascaded through connected systems. The surface and the bed were not two separate domains linked by a slow, passive transfer of meltwater. They were dynamically coupled in ways that could amplify disturbances across the full thickness of the ice sheet within days. The practical consequence of this coupling was severe. It meant that a warming climate would not merely change the Arctic gradually, giving researchers time to study it in one state before it transitioned to another. It meant that warming events, extreme melt seasons, prolonged heat waves of the kind that were already becoming more frequent, could trigger rapid reorganizations of the subglacial drainage system. Features that had been stable for decades could destabilize suddenly. Lakes that appeared on a planning map one year could be gone the next, and the changes happening to those features were not simply a matter of one lake draining and another filling. They were connected to shifts in how the entire glacier moved, how much mass it delivered to the ocean, and how quickly sea level would respond. This created a genuinely uncomfortable situation for the scientific programs designed to study these environments. The argument for investing in subglacial access had always included the premise that what lay beneath the ice was ancient and preserved, a record of past conditions that would reward careful, patient investigation. That argument remained valid in a general sense. The sediments at the base of subglacial lakes did contain climate records. The biology, if present, did reflect the long evolutionary history of those sealed environments. But the sealing was less permanent than it had appeared. The preservation was conditional. And the conditions under which it depended, the stability of the overlying ice and the pressure equilibrium of the subglacial drainage network, were themselves being altered by the very warming that made studying the ice sheet's dynamics so urgent. The programs that had been designed around patient long-term access were now racing against an environment that was reconfiguring itself faster than they could plan missions to study it. The instrument development timelines that had seemed acceptable when the ice was assumed to be broadly stable now looked dangerously slow against an ice sheet that might be reorganizing its drainage at a rate that would outpace any program built on decade-long development cycles. Researchers began to argue more forcefully for a different approach, not slower and cleaner, but faster and more adaptive. Not single large missions aimed at fully characterizing a single target, but networks of simpler instruments deployed across multiple sites, capable of detecting and responding to dynamic changes in real time. The argument had merit, but it ran into a wall that had nothing to do with science. Faster and more adaptive still meant penetrating the ice. It still meant building systems that could operate without contaminating pristine environments. It still meant solving the communication problem, because a real-time monitoring network was useless if the sensors in it could not transmit data through the ice above them. Acoustic communication through water was possible but limited in bandwidth. Fiber optic cables could carry large amounts of data but were vulnerable to being severed as the ice moved. Electromagnetic signals at frequencies low enough to penetrate thick ice existed in principle, but required antenna systems that were difficult to deploy in the field and that transmitted slowly. None of these solutions was satisfying. All of them involved significant compromise, and the compromise that each required was different enough that no single design worked for all scenarios. Underneath all of this technical and logistical complexity lay a simpler truth that was becoming increasingly difficult to avoid. The model of exploration that had served science so well in accessible environments, characterize it thoroughly, return with samples, was not transferable to the subglacial world without modifications so extensive it amounted to a different model entirely. The environment was not cooperating. It was not simply challenging, it was actively and continuously defeating the assumptions on which the standard exploration model rested. It moved when it needed to stay still. It changed when it needed to remain constant. It hid its most important features in the places that were hardest to reach and most sensitive to disturbance. And this was the moment when the question at the center of this documentary stopped being purely about engineering or funding or logistics. It became a question about the relationship between the speed of curiosity and the pace at which the physical world permits curiosity to be satisfied. Because the Arctic was changing rapidly. The window for studying what lay beneath its glaciers in anything close to its current state was not open indefinitely. The clock was running, and the systems needed to answer the questions before the answers themselves changed were still being designed, debated, and tested in laboratories far from the ice. What had started as a scientific puzzle was becoming a race. And the terrain of that race, the moving, pressurized, lightless labyrinth beneath the North Pole's glaciers, was tilting steadily against every team that entered it. The institutions that fund science move slowly by design. Peer review, budget cycles, multi-year grant frameworks, these are not bureaucratic failures but considered choices, meant to filter out noise and protect the integrity of long-term investment. But when the environment being studied begins changing faster than the institution studying it can adapt, that deliberate slowness becomes a structural problem. And by the early years of the second decade of this century, that is precisely what polar science was confronting. Program directors at the major funding bodies, the National Science Foundation, the Natural Environment Research Council in the United Kingdom, the European Research Council, began receiving reports from the field that did not match the assumptions built into the programs they had already approved. Subglacial systems that had been characterized as stable enough for phased, multi-year instrument deployment were showing evidence of reorganization between field seasons. Access corridors that existed in one year's radar survey were absent or displaced in the next. The models that had justified investment in specific engineering solutions were built on data sets that were already becoming historical artifacts before the engineering was complete. This created a dilemma that had no clean resolution. To acknowledge the problem openly was to invite scrutiny of past funding decisions. To ignore it was to continue spending on approaches that researchers in the field were quietly losing confidence in. What emerged, as it often does in institutions under pressure, was a middle path. Continued investment in existing programs combined with commissioning of reviews, working groups, and strategic reassessments that could absorb the uncertainty without forcing immediate decisions. The working groups were not without value. They brought together glaciologists, engineers, remote sensing specialists, and program managers in structured conversations that would not otherwise have happened. They produced frameworks for thinking about the coupling between surface processes and subglacial dynamics that improved how the community understood the problem. But they also took time, and time, in a system accelerating toward change, was the one resource that could not be created by committee. For programs already in development or in the field, the consequences were concrete and in many cases painful. Instrument packages designed around access to stable, slowly evolving water bodies had to be reconsidered when those water bodies proved to be transient features of a dynamic drainage system rather than permanent reservoirs. Vehicles engineered to specific geometric constraints, borehole diameters, pressure tolerances calibrated to particular depth targets, faced the possibility that those targets had shifted before deployment was complete. In some cases, field campaigns proceeded anyway, because the logistics had already been committed, the personnel mobilized, the equipment shipped. The results were scientifically useful but incomplete in ways that had not been anticipated, and the incompleteness itself became data. From evidence of how thoroughly the original model had underestimated the system's dynamism. Timeline stretched. In a field where a single field season represents 12 months of waiting and preparation, a 2- or 3-year extension is not a minor adjustment. It is a fundamental change to the career mathematics of the researchers involved, to the continuity of graduate student cohorts, to the institutional relationships between universities and the funding bodies that depend on demonstrable progress to justify continued support. Programs that had promised deliverables by certain dates found themselves renegotiating not just schedules, but the definition of success itself. Into this environment of institutional strain came a debate that had been building for years, but now moved to the center of the community's attention. The question was not whether to study the subglacial environment. That consensus held, but how. 2 positions had crystallized, and both had serious people behind them. The first position argued that the priority should be remote sensing. Satellites carrying synthetic aperture radar could image subglacial topography through kilometers of ice. Airborne platforms could deploy ice-penetrating radar across continental scales in a single field season. These systems could not enter the subglacial environment, could not sample its water or retrieve its microbial communities, but they could track it. They could map the drainage network as it changed, identify where water was accumulating and where it was being discharged, follow the evolution of subglacial lakes as they filled and drained over monthly and annual timescales. In a system reorganizing faster than direct access missions could follow, the argument went, the most urgent scientific need was the ability to observe that reorganization. Spending resources on engineering access to targets that might not remain stable long enough to be reached was, from this perspective, a form of institutional optimism that the data no longer supported. The second position acknowledged the value of remote sensing, but argued that there were things radar could never tell you. It could not characterize the chemistry of subglacial water. It could not determine whether the microorganisms detected in outflow samples during flood discharge events were representative of the broader subglacial community or artifacts of transport and dilution. It could not resolve the question of how life was sustained in permanent darkness under enormous pressure without any surface energy input. These were not peripheral questions. They were the scientific core of why subglacial research mattered, and they required direct access. Retreating to remote sensing alone was, from this perspective, accepting a permanent location that would leave the most important questions permanently unanswered. Both arguments had costs that their proponents did not always acknowledge fully. The remote sensing path risked creating an increasingly sophisticated map of a system science could observe but never touch, a kind of permanent voyeurism that accumulated structural knowledge while the biological and geochemical questions remained open. The direct access path risked continuing to invest in engineering solutions whose targets were shifting, spending decades building capability for a system that by the time the capability was ready might be fundamentally different from the one that had motivated the investment. The debate never fully resolved. What it produced instead was a reallocation of emphasis that satisfied neither side completely but reflected the genuine difficulty of the choice. Remote sensing programs received increased support, and the data they generated was remarkable. Continental scale maps of subglacial hydrology, time series of lake volume change, evidence of drainage events that released water from beneath the ice in volumes large enough to affect ocean circulation. These were not small findings. But the direct access programs continued as well, scaled back in some cases, redirected in others but not abandoned. And then the third pressure arrived, or rather, it had always been present, but its urgency became impossible to ignore. The ice was thinning. Not everywhere and not uniformly, but across the high Arctic and across Greenland in patterns that matched the projections of climate models with a precision that was uncomfortable to contemplate. Subglacial environments that had been sealed under several kilometers of ice for tens of thousands of years were in some areas coming within reach of surface processes for the first time since before human civilization existed, and that proximity was not creating opportunity. It was creating contamination in both directions. Surface meltwater infiltrating previously isolated systems carrying organic material and microorganisms that had no prior contact with the subglacial world, and subglacial water reaching the surface in places and at rates that had no analog in the observational record. The archive was shrinking. Researchers who had spent careers trying to reach pristine subglacial environments were confronting the possibility that pristine, in the strictest scientifics, was already a historical category for some of the most accessible targets. The systems that were easiest to reach were, by virtue of being easier to reach, also the most exposed to the changes happening at the surface. The truly isolated environments, the ones that might still offer genuinely uncontaminated records of ancient biology and chemistry, were deeper, colder, less accessible, and the tools to reach them were still under development. This was the context in which planetary science brought its full weight to bear. NASA's interest in subglacial research on Earth was no longer purely academic. It was directly tied to the scientific justification for billion-dollar missions to the outer solar system. Europa Clipper and the JUICE mission were moving through development phases with launch windows that could not be delayed to wait for Earth-based subglacial science to resolve its foundational questions. If researchers could not characterize what life looked like in an Earth analog for a Europan ocean, interpreting data from those spacecraft's instruments would be severely constrained. The connection was explicit, and the funding followed it. Proposals that framed Earth subglacial research in terms of planetary analog science moved through review with a momentum that purely Earth science proposals had not been generating. But the connection to planetary exploration also brought planetary protection standards into the conversation in ways that complicated fieldwork. Contamination standards tightened. The engineering requirements for access systems became more demanding not just because the target environments were difficult, but because the downstream applications of the science demanded a level of cleanliness that had not previously been part of glaciological fieldwork. It was within this constellation of pressures, institutional strain, methodological debate, accelerating environmental change, and the gravitational pull of planetary science that a quieter strategy began to take shape. Researchers who had been working on the hard problem of deep subglacial access began turning their attention toward environments that were accessible now, that were comparable without being identical, and that could serve as proving grounds for instruments, protocols, and conceptual frameworks before they were committed to targets that might not remain stable long enough to be useful. The logic was not one of defeat, it was closer to reconnaissance, understanding the terrain before committing the main force. Shallow subglacial systems in Iceland, where geothermal heat created liquid water environments beneath ice that could be reached without years of specialized drilling. Arctic fjord interfaces, where the boundary between freshwater ice and marine saltwater created chemical and biological gradients that echoed what theory predicted for deep subglacial systems. The lake sediments of Antarctic dry valleys, where ancient microbial communities had survived for millions of years under conditions that pushed at the boundaries of what biology was understood to tolerate. These were not the target. Everyone in the field understood that. But they began producing results that were not merely preparatory. The instrument packages deployed in accessible subglacial systems came back with data on microbial community structure under permanent darkness that revised the theoretical models used to interpret remote sensing returns. The chemical profiles from fjord interfaces suggested that the geochemical energy sources available in deep subglacial systems were more diverse than the models had assumed, which meant that biological activity at depth might be more widespread and more complex than the cautious estimates had allowed. The dry valley sediment records began filling in a temporal picture of how subglacial microbial communities responded to episodes of hydrological change over geological time, a baseline that would be essential for distinguishing ancient biological signatures from recent contamination in any future direct access sample. The questions were not answered, but they were beginning, for the first time, to be asked with enough precision that answering them seemed like a tractable problem rather than an aspiration. From what the analog science strategy produced at its best was a new kind of humility about what the deep subglacial environment would actually require of the instruments sent into it. This was not a small thing. From the history of exploration is filled with missions that failed not because the engineers were incompetent, but because the designers had imagined the target incorrectly. They had built for what they expected to find rather than for what was actually there. From the analog programs were systematically correcting that error before it became catastrophic and expensive in the wrong place. The Iceland work in particular yielded something unexpected. From researchers studying liquid water environments beneath relatively thin Icelandic glaciers, where geothermal heat kept basal zones liquid year-round, found that the microbial communities in those accessible systems were not distributed uniformly. They were patchy. From dense in some locations, nearly absent in others, organized around chemical gradients and physical features of the bedrock that were invisible from the surface. The implication was significant. From any access mission that punched a single borehole into a subglacial lake and sampled the water at that point was not necessarily characterizing the lake. It was characterizing one location within the lake, and that location might be representative of the whole or might be an outlier. From without a way to map the spatial variability of the system before sampling it, single-point access missions were generating data that was difficult to interpret with confidence. This had been suspected before, but the Iceland data gave it specificity. From it was no longer a theoretical concern but a demonstrated pattern in real subglacial water, accessible enough to be studied repeatedly across different seasons and different ice thicknesses. From the spatial patchiness of subglacial microbial communities was real, it was structured, and it meant that the engineering challenge of subglacial access was even more demanding than the single access point model had assumed. A mission that could reach a lake through a single borehole was necessary but not sufficient. From what was ultimately needed was something closer to a distributed survey, multiple access points or mobile vehicles capable of traversing the full extent of a subglacial water body. From that required not a borehole but several, or a vehicle that could enter through one and explore far beyond it without losing contact with the surface. The second-order consequence of this realization was a renewed argument for the cryobot concept. From a probe that melted its own path through the ice and carried its instruments directly into the subglacial water, without depending on a borehole that had been drilled from above and that was already refreezing behind it, would not be constrained to a single sampling point. From it could, in theory, move through the water after descending, covering enough ground to capture some of the spatial variability that single-point access missed, but the cryobot remained a concept under development, not a deployable system. From and the engineering challenges it faced were formidable in ways that the analog science results had clarified rather than resolved. Power was the fundamental constraint. A cryobot descending through 3 kilometers of ice at a rate of meters per day would require sustained power output for weeks or months. From battery technology at the scale required for that mission duration was not mature enough to fit within a vehicle small enough to fit through a practically sized borehole, let alone one that melted its own access channel. From nuclear power sources, the technology that planetary scientists had long discussed for deep ice missions on other worlds, offered the energy density that batteries could not match. From but deploying nuclear power sources in field environments in the Arctic, with all the regulatory, logistical, and public acceptance challenges that entailed, was a different kind of problem entirely. It was not purely an engineering problem. From it was a political and institutional one, and those problems moved on timescales that made the engineering timelines look short by comparison. The communication constraint was equally intractable. From a cryobot descending into ice and water, carrying a fiber optic tether that unreeled behind it as it descended, could in principle maintain a data link to the surface. Fiber optic cables were capable of transmitting large volumes of data and were not blocked by the ice the way radio signals were. But the tether created its own problems. It had to be long enough to reach the full depth of descent, which meant carrying kilometers of cable inside the vehicle before deployment. It had to survive being dragged through refreezing ice as the borehole closed around the upper portions of the descent path. And if it broke, which was a realistic possibility given the mechanical forces involved, the mission became autonomous without warning, with no way to retrieve data until the vehicle physically returned to the surface, if it could return at all. Researchers working on the communication problem began exploring alternatives. Low-frequency electromagnetic signals could penetrate ice if generated with enough power, but the bandwidth they offered was extremely limited, sufficient perhaps to transmit a status signal and a small volume of compressed data, not a continuous scientific stream. Acoustic communication through the ice was possible but degraded with distance and was susceptible to interference from the mechanical noise generated by the vehicle itself. None of these alternatives was satisfactory. The communication problem, like the power problem, remained open, and it remained open in ways that were becoming better characterized but not closer to resolved. Meanwhile, the wider consequences of the pivot were propagating into communities that had not previously been closely engaged with subglacial science. Climate modelers, whose work on sea level rise projections had always included subglacial dynamics as one of the largest sources of uncertainty in their outputs, began publishing more explicitly about what that uncertainty meant for practical planning. The range of plausible sea level rise by the end of the century was wide, and a significant part of that width came from not knowing how the Greenland ice sheet's basal drainage system would respond to continued warming. That uncertainty was not a modeling failure. It was a reflection of observational gaps that the modeling community could not fill with mathematics. The data simply did not exist. And the institutions that needed sea level projections for infrastructure planning, coastal management, and risk assessment were beginning to express that frustration in terms that funding agencies could not ignore. The Arctic Council, the intergovernmental forum that coordinates policy among the 8 Arctic nations, had maintained working groups focused on Arctic science for decades, but the urgency with which those working groups discussed subglacial research elevated perceptibly in this period. The connection between what happened at the glacier bed and what happened to coastal communities in Bangladesh, in Florida, in the Netherlands was not new knowledge. But it was arriving with new insistence in policy discussions, partly because the rate of ice loss was accelerating beyond previous projections, and partly because the most recent assessments of sea level risk were explicitly flagging subglacial dynamics as the element of the system least constrained by available data. This broader attention brought resources, but it also brought expectations that the scientific community struggled to meet on the timescales that policy processes demanded. Governments planning infrastructure with a 50 or 100-year horizon wanted to know, within some reasonable range of confidence, what sea levels would be at the end of that horizon. The honest answer from the scientific community that the uncertainty in that number was substantially larger than anyone wanted it to be, and that reducing the uncertainty required access to subglacial environments that current technology could not reliably provide, was accurate but unsatisfying. The gap between what the policy process needed and what the science could deliver was not a gap that better communication could close. It was a gap that required the engineering problems to actually be solved. And this is where the contradiction at the heart of the whole enterprise became most visible. The case for investing in subglacial access technology had never been stronger. The policy need was clear, the scientific rationale was compelling, the planetary science connection was providing new funding pathways, and the analog programs were generating the baseline data that would be needed to interpret results from direct access missions. Everything pointed toward acceleration. Faster development, more ambitious field campaigns, broader international coordination. But the environment itself was moving in the opposite direction. Each year of delay was not a neutral pause. It was a year in which the subglacial systems that were easiest to access became less pristine. A year in which the drainage network beneath the ice reorganized in ways that invalidated existing target characterizations. A year in which the ice above the most important deep targets thinned by amounts that changed the pressure conditions any access system would need to be engineered for. The targets were not simply waiting. They were changing, and the direction of change was generally toward conditions that made them harder to study usefully, not easier. There was also a consequence that received less attention than the logistical and scientific challenges, but that was in some ways the most significant of all. The very success of the analog science strategy, its demonstration that accessible subglacial environments could yield genuine insights into the biology and chemistry of the deep system, created a new temptation. If the accessible systems were informative enough, if they produced results that could be published, that could justify continued funding, that could satisfy the external stakeholders who needed the science to be demonstrably progressing, then the pressure to commit to the harder, more expensive, more technically uncertain direct access missions diminished. Not disappeared, but diminished. The accessible environments were delivering returns. The deep environments were still promising future returns, and in any resource-constrained system, demonstrated returns compete effectively against promised ones. The risk was subtle but real. A research community that settled into studying what it could reach, while perpetually developing but never deploying the tools for what it needed to reach, would produce knowledge that was genuinely valuable but perpetually incomplete. It would generate a literature about accessible analogs that was increasingly sophisticated, and a literature about the deep subglacial environment that remained thin, indirect, and bounded by the limits of remote sensing. The fundamental questions about the biology of permanently isolated dark water ecosystems, about the geochemical record preserved in ancient subglacial sediments, about the mechanics of the basal zone under full glacial pressure would remain open. Not because they were unanswerable, but because the system of incentives was not adequately rewarding the people willing to pursue the answers in the places where the answers actually resided. Recognizing this dynamic was one thing, changing it was another. Because the people most aware of the problem were also the people most invested in the programs that embodied it, and the institutions that could have changed the incentive structure were the same ones that had settled into the middle path of sustained ambiguity. The situation was not a conspiracy or a failure of individual will. It was a structural outcome of rational responses to genuine uncertainty, and structural problems of that kind tend to persist until something external forces them to a head. Something that can no longer be absorbed by working groups and strategic reviews and incremental progress in accessible environments. Something that makes the incompleteness of the existing knowledge suddenly undeniably costly in a way that demands a different response. That pressure was building. Quietly, in the data streams from satellites monitoring ice sheet elevation, in the records of summer melt extent, in the increasingly urgent language of assessment reports on sea level risk. The situation was larger and more deeply rooted than any single program had the capacity to address. And the window for studying the subglacial world in anything close to its current form was not narrowing gradually. It was accelerating toward a threshold that no one could precisely locate, but that everyone in the field could feel approaching. The threshold that everyone could feel approaching arrived, not as a single event but as a convergence of data streams that arrived within a few years of one another and that, taken together, were impossible to absorb without revising every assumption the field had been working from. The first came from the ice cores. For decades, ice cores extracted from Greenland's interior had been the crown jewel of paleoclimate research. Each layer of compressed snow was a year's record of atmospheric conditions, preserving bubbles of ancient air, traces of volcanic eruptions, signatures of solar activity, and concentrations of greenhouse gases stretching back hundreds of thousands of years. The deepest cores, drilled at sites like Summit Central Greenland, had reached ice more than 100,000 years old. That record was remarkable, irreplaceable, and it had been used to reconstruct the history of Earth's climate with a precision no other archive could match. But the ice cores had a limit. They stopped at the bottom of the ice sheet. They could not reach the sediment beneath the ice, and the sediment was where the longest climate records were stored, undisturbed layers of material deposited over millions of years before the current ice sheet existed in its present form. Geologists who studied other regions of the planet could reach million-year-old sediment records by drilling into lake beds or ocean floors. In Greenland, those sediments were buried under 3 kilometers of moving glacial ice. Reaching them was not simply a matter of drilling deeper. It required penetrating the full thickness of the ice sheet without having the borehole collapse, breaching the basal melt layer, passing through it without catastrophic contamination, and then drilling into the sediment below, which might be waterlogged, unstable, or under pressures that defeated conventional sampling equipment. What researchers began to understand with increasing clarity was that the sediment record beneath the Greenland ice sheet held answers to questions that the ice core record alone could not resolve. One of the most significant was the history of the ice sheet itself. The ice cores recorded climate, but they could not directly show whether the Greenland ice sheet had existed continuously since the last major ice age, or whether it had partially or wholly melted during previous warm periods and then regrown. That distinction mattered enormously. If the ice sheet had survived previous warm periods intact, models of its future behavior could draw on that history as evidence of resilience. If it had collapsed, partially or completely, during warm periods comparable to what was now being projected for coming centuries, then its future was far less stable than the most optimistic models assumed. The sediment record could answer that question. Glaciated bedrock produces a distinctive chemical and physical signature in sediment. Exposed, unglaciated bedrock produces a different one. Layers of sediment bearing the signatures of an ice-free surface, buried beneath layers bearing the signatures of glaciation, would mean that the ice sheet had come and gone. And if that had happened during a warm period in the past, it was evidence that it could happen again. Accessing that sediment record was exactly the kind of mission that was beyond current technical capability. But indirect evidence had been accumulating from other sources. Cosmogenic isotope analysis of rocks exposed at the edges of the ice sheet, rocks that had been submerged beneath ice and then exposed as glaciers retreated, could measure how long those surfaces had been exposed to cosmic radiation. That exposure history could be used to reconstruct the extent of the ice sheet over time. And what those analyses were beginning to suggest was that during the last interglacial period, roughly 120,000 years ago, when global temperatures were perhaps 1 to 2 degrees Celsius warmer than the pre-industrial average, the Greenland ice sheet may have been substantially smaller than it is today, not gone entirely, but reduced enough to have contributed several meters to global sea levels. The implication was not subtle. The temperature anomaly of the last interglacial was within the range of what the current warming trajectory was projected to reach within this century. Not at its end, but partway through it. If the ice sheet had been significantly reduced during the last interglacial, the question was not whether it could be destabilized by current warming. The question was how quickly destabilization would unfold and how much the subglacial processes, the ones that remained poorly understood and inaccessible, would control the pace. This recontextualized everything that had come before. The debate about whether to prioritize remote sensing or direct access. The analog science strategy and its productive but incomplete results. The engineering programs developing borehole systems and cryobots and autonomous vehicles. All of it was oriented toward understanding a subglacial environment whose behavior over geological time had now been shown, tentatively but with increasing confidence, to be far more variable than the engineering programs had been designed around. The ice sheet was not a permanent fixture with a dynamic drainage system sitting beneath it. It was itself a dynamic system, one that had grown and contracted and potentially collapsed in response to climate changes smaller in magnitude than the ones currently underway. And here the second convergence arrived. The GRACE satellite mission, which had been measuring changes in Earth's gravitational field as a proxy for ice mass since 2002, and its successor GRACE-UFO, launched in 2018, had been producing a record of Greenland ice mass change that was already alarming. But when researchers applied more sophisticated analysis to that record, decomposing the signal into contributions from different parts of the ice sheet, they found something that the aggregate numbers had partially obscured. The mass loss was not distributed evenly. It was concentrated at the margins in the outlet glaciers that drained the interior of the ice sheet into the surrounding ocean, and those outlet glaciers were not losing mass primarily through surface melt. They were losing it dynamically through acceleration and thinning driven by the interaction between their bases and the warming ocean water intruding into the fjords they calved into. That interaction happened at the grounding line, the boundary where the glacier transitions from resting on bedrock to floating on water. The grounding line was a place where subglacial processes directly determined how the glacier calved, how fast it flowed, and how much ice it delivered to the ocean. And the grounding line was almost entirely inaccessible. It existed in deep water beneath the calving front of outlet glaciers, in regions where the ice-ocean interface was too dynamic and too dangerous for any current observational platform to approach directly. The processes happening there, the warm water melting the underside of the ice, the changing basal pressure as ice thinned and began to float, the migration of the grounding line itself inland as the glacier retreated, were being inferred from satellite observations and model outputs rather than measured directly. What the GRACE data, combined with glacier velocity measurements from satellite radar, was showing was that grounding line retreat in some of Greenland's major outlet glaciers was occurring faster than the models had projected, not by a small margin, by factors that suggested the models were missing processes or incorrectly parameterizing ones they included. The most likely explanation was that the subglacial hydrology, the drainage system that influenced how efficiently meltwater reached the grounding line and how it modulated basal friction, was behaving in ways that were not captured in the models because the data needed to constrain those behaviors did not exist. Because no one had been able to get there to measure it directly. The circle closed with uncomfortable completeness. The biggest uncertainty in sea level projections came from dynamic ice loss. Dynamic ice loss was controlled partly by processes at the grounding line. Grounding line behavior depended on subglacial hydrology. Subglacial hydrology could not be characterized with adequate precision because direct access to the relevant environments remained technically beyond current capability. And the gap between current capability and required capability was not closing fast enough, given the rate at which the system was evolving. The third convergence came from biology, and it was the one that most fundamentally changed the interpretive frame. Researchers analyzing meltwater discharge from Greenland outlet glaciers during summer drainage events had been collecting microbial samples for years. The communities in those samples were diverse and metabolically active. But a more systematic analysis of those communities, comparing samples from different glaciers, different seasons, and different depths within the subglacial drainage system, revealed a pattern that had not been anticipated. The microbial communities in subglacial outflow were not homogeneous. They varied significantly from glacier to glacier, and the variation was structured in ways that correlated with the bedrock geology beneath each glacier rather than with surface conditions above it. That correlation meant that the microbes were not simply surface organisms that had washed into the drainage system with meltwater. They were indigenous, adapted to the chemical environment produced by the specific minerals in the bedrock beneath each glacier. They were, in a meaningful sense, ancient. They had evolved in contact with those rocks, in isolation from the surface world, over timescales that were long enough to produce measurable divergence between communities beneath glaciers sitting on different rock types only a few hundred kilometers apart. The isolation was real. The evolution it had enabled was real, and the depth of that evolutionary divergence when researchers began estimating it using molecular clock methods suggested that some of these communities had been accumulating genetic differences from their surface relatives for tens of thousands of years, possibly longer. This was the biological finding that made the case for direct access unavoidable, not just useful, not just scientifically interesting, but unavoidable. Because if subglacial microbial communities beneath Greenland had been evolving in isolation for tens of thousands of years, then they constituted a biological archive of extraordinary value. An archive of how life adapts to darkness, pressure, mineral chemistry, and geological change over timescales that connected the present to the last ice age and beyond. That archive was not being preserved by the warming climate. It was being eroded by it. Every drainage event that flushed subglacial water and its biological cargo out to the ocean was destroying a portion of that record irreversibly. Every year of warming that changed the chemical environment at the glacier bed was selecting against the organisms most tightly adapted to previous conditions. From the archive was being read by the erosion it was suffering, and the reading was partial, indirect, and uncontrolled. To read it properly required going there, not sending water down a borehole and collecting what washed back up. From going there, into the water, into the sediment with instruments capable of resolving spatial variation, measuring chemical gradients, collecting community samples from multiple points within the same system, and returning that information to people who could interpret it against the geological and glaciological. From context, that required a vehicle that could descend through kilometers of ice, enter a subglacial lake, navigate within it without constant communication with the surface, collect meaningful samples without contaminating what it touched, and either return or transmit its data through the ice above it. From every component of that mission existed in some form. The descent technology existed at the prototype level. The navigation systems existed in more developed forms for open water applications. The sampling equipment existed as laboratory instruments that had not yet been miniaturized for field deployment. From the communication systems existed as concepts rather than proven hardware. From what did not exist was the integration of all of those components into a single coherent system that had been tested under realistic conditions, and that could be deployed reliably in the field within a time frame that still allowed for meaningful science before the targets changed beyond recognition. From that was the challenge that the field was now carrying. Not a lack of vision, not a lack of scientific motivation, not even a lack of funding, though funding remained constrained. The challenge was integration at scale under time pressure for an environment that would not wait and did not negotiate. From and somewhere in that challenge, in the gap between what was needed and what was possible, lay the exact shape of why the North Pole's hidden world remained beyond our reach. From the shape of the challenge, once laid out with that kind of clarity, did something that challenges of this magnitude sometimes do when they are finally articulated precisely enough. It stopped being paralyzing and started being generative. From the scientific community had spent years circling the problem, approaching it from different angles, retreating when the technical obstacles proved too large, redirecting toward accessible analogs, and watching the target change beneath every plan. But by the time the biological evidence of genuine long-term isolation was combined with the paleocolumate evidence of ice sheet instability and the GRACE data on accelerating dynamic mass loss, the argument for treating subglacial access as a first-order engineering priority, rather than a desirable eventual capability became difficult to counter on any rational basis. What changed in the programs that followed was not dramatic in the way that public narratives about scientific breakthroughs tend to be. There was no single moment of invention, no eureka discovery in a laboratory that solved the descent problem overnight. What changed was the organizational structure of the effort. Programs that had been developing components in relative isolation began pooling their work in a more coordinated way. The glaciologists who understood the target environment began working directly and continuously with the engineers developing the access systems, rather than providing specifications at the beginning of a development cycle and receiving a prototype years later that was built for a target that no longer matched the current understanding of the environment. The planter scientists who had been thinking about ice-penetrating systems for Europa and Enceladus brought engineering approaches that had been developed under the stringent constraints of space mission design, approaches that prioritized reliability, contamination control, and autonomous operation in ways that, terrestrial drilling programs had not always required. This cross-disciplinary integration was not seamless. Different scientific cultures carry different assumptions about acceptable uncertainty, about what constitutes a successful test, about when a system is ready to be deployed in the field versus when it requires further development. The glaciologists were accustomed to field conditions that were brutal but in principle reachable by conventional logistics. The planetary scientists were accustomed to designing for conditions that could not be tested on Earth at all, for environments where the first real test was the mission itself. Bridging those cultures required explicit negotiation about standards and expectations that individual disciplines had previously taken for granted. But the negotiation produced something valuable. It forced the terrestrial programs to articulate, with a precision they had not always maintained, exactly what they needed their systems to do, in what sequence, under what conditions, and with what margins for error. And it forced the planetary scientists to confront the differences between designing for a single unrepeatable mission and designing for a program that would need to be executed multiple times across different field seasons and different target environments, that would need to be maintained, repaired, and upgraded by field teams working in temperatures that froze batteries and seized mechanical components without warning. The result, emerging from this period of intensified collaboration, was a new generation of concept designs for subglacial access systems that were more modular, more robust, and more explicitly constrained by what the environment would actually permit, rather than by what the designers hoped it might permit. The borehole problem, the persistent tendency of ice under pressure to refreeze around anything inserted into it, was addressed not by trying to keep single large borehole open for extended periods, but by redesigning the mission architecture around a vehicle that could descend through a relatively narrow melt channel and function independently once it reached the water below. The communication problem was partially addressed by accepting the limitations of acoustic signaling through ice and designing data compression and prioritization protocols that could extract the highest value scientific information from a limited bandwidth connection, rather than trying to transmit a continuous, high-resolution data stream that the physics of the medium could not support. The contamination problem, which had always been the most intractable because it was governed by biology rather than engineering, was addressed through a combination of improved sterilization protocols developed from the planetary protection standards and a reconceptualization of what sterile access actually required. The previous standard had aimed at introducing zero foreign microorganisms into a subglacial environment. That standard was almost certainly impossible to meet in practice, because modern field environments contained microbial life in every air mass, every water droplet, every surface that was not maintained under cleanroom conditions. The revised standard, informed by the analog science work, aimed instead at introducing foreign organisms at concentrations so low that indigenous communities could not be detectably affected, and at documenting what was introduced so that contamination could be accounted for rather than assumed absent. It was a more honest standard and, critically, a more achievable one. These were not small shifts, they represented a fundamental maturation of the field's understanding of what it was actually trying to do and what was actually possible. The earlier programs had sometimes been built on an implicit assumption that subglacial environments were waiting to be entered in a pristine state, and that the scientific payoff would arrive once the engineering obstacle was overcome. The revised understanding acknowledged that the environments were dynamic, that pristine was a relative term that required explicit definition for each target and each question, and that the scientific payoff would depend as much on the quality of the contextual data surrounding the access event as on the samples. Collected during it, that contextual data requirement changed what a complete subglacial access mission looked like. It was no longer sufficient to drill a hole, lower instruments, collect samples, and analyze them in isolation. A mission that aimed to answer meaningful scientific questions needed to characterize the ice above the target in detail before descent, to map the subglacial topography and hydrology of the area, using airborne radar and satellite altimetry over multiple seasons before committing to a drill site, to monitor the surface above the target throughout the field campaign, to detect drainage events or pressure changes that might alter conditions at the bed, and to analyze the meltwater discharged from the glacier system in the weeks surrounding the access event to establish the baseline chemistry and biology against which subglacial samples would be compared. This expanded scope meant that a single field season was not enough. A meaningful subglacial access mission was a multi-year program that built its own baseline before attempting access, that treated the preparation as science rather than logistics, and that was designed from the outset to be interpretable within its broader glaciological and climate context. That was a more expensive and more demanding program than the earlier concept of drilling through ice and collecting what was found. But it was also a more honest one, and the scientific community's increasing willingness to design for that standard reflected how much the field had learned from its earlier attempts. The consequence for the timeline was significant. Multi-year preparation before access meant that the missions now being designed were not going to reach their targets in the near future. The systems under development were aimed at field deployment further out on the horizon than any of the programs that had preceded them. That delay was frustrating given the urgency of the questions being asked, and it was not without cost. Every year of preparation was a year in which the target environment was continuing to change, a year in which the biological archive being sought was continuing to be eroded by the same warming that was driving the scientific urgency in the first place. But the alternative, deploying systems that were not ready, that would reach the target and fail to produce interpretable results because the contamination controls were inadequate, or the spatial sampling was too limited, or the communication link collapsed before meaningful data was retrieved, was worse. A failed access mission did not simply lose the data it was designed to collect. It consumed the logistical and financial resources that would have funded the next attempt. It damaged the credibility of the program in the eyes of the funding bodies that needed to authorize continued investment. And in the worst cases, it contaminated the target environment in ways that compromised the scientific value of any future access attempt. The cost of failure in this environment was not just the cost of the failed mission, it was the cost of everything that depended on the trust that mission was supposed to build. The question that remained, and that could not be answered by better program design alone, was whether the ice sheet that these missions were being designed to study would still be recognizable as the same system by the time the missions were ready to access it. This was not a theoretical concern. Specific outlet glaciers that had been stable at the beginning of the remote sensing record were by now retreating at rates that would have their grounding lines tens of kilometers inland from their current positions within the lifetime of the programs being designed to study them. Subglacially lake systems that had appeared stable in the ISAT record were showing drainage signatures in more recent data. The deep interior of the Greenland ice sheet, the most stable part of the system and the most likely location for the ancient isolated subglacial environments that held the richest biological archives, was also the hardest reached logistically, most distant from field support infrastructure, and the most sensitive to the communication and power constraints that the new designs were still working to solve. The honest accounting of where things stood, by the time the collaborative programs had produced their revised system concepts and their more realistic deployment timelines, was this. The science was clearer and more compelling than it had ever been. The engineering was more mature and more honestly constrained than it had been in previous program generations. The institutional structures supporting the work were better coordinated across disciplines and across national programs. The case for investment was stronger, and the understanding of what that investment needed to deliver was more precise, and the environment beneath the ice remained beyond reach. Not forever, not in principle. But in practice, at the level of direct access that would allow the most important questions to be answered, the barrier had not fallen. It had been better characterized, better understood, and more honestly confronted. The specific obstacles had been named and their properties had been measured. The path through them had been identified at least in outline, but the path had not yet been walked, and the conditions at the other end of it were changing faster than the progress toward it. What this meant for the central promise of the documentary, the question of why we cannot truly explore beneath the North Pole's glaciers, had at this point been answered in its most important dimension. The answer was not a single thing, it was a system. Pressure that exceeded the tolerance of conventional materials. Ice that flowed and refroze around anything inserted into it. Darkness that defeated the sensors we depended on. Communication channels that the physics of the medium refused to support at useful bandwidth. Contamination risks that could not be reduced to zero and that required explicit accounting rather than elimination. A target environment that was dynamic, spatially variable, and coupled to surface conditions in ways that made the window of stable access narrower than the preparation time required. a climate that was accelerating all of those dynamics simultaneously while reducing the time available to study the environments before they changed beyond the state that motivated the study. These were not separate problems that would be solved one at a time in sequence. They were interconnected constraints that needed to be addressed simultaneously in a coordinated program, on a timeline set not by the convenience of the researchers, but by the pace of environmental change that was continuing regardless of how the programs were progressing. The gap between what was needed and what was possible had narrowed, but it had not closed. And the distance remaining was still measured in years of development, years of preparation, years of field campaigns that would each teach something new about the environment, while edging incrementally closer to the direct access that remained the ultimate goal. The ice above those hidden worlds was thinner than it had been. The water beneath them was warming. The biological communities that had been evolving in isolation for tens of thousands of years were beginning to be disturbed by the drainage events and chemical changes that a warming climate was introducing. The sediment record was accumulating new layers deposited under conditions that were different from anything in the archive below them, layers that would complicate future interpretations of the ancient record. The labyrinth was changing. Not on human timescales, not in ways that were visible to the naked eye, but in ways that were unmistakable in the satellite data and the outflow chemistry and the molecular clock estimates of microbial divergence. The hidden world beneath the North Pole's glaciers was not the same world it had been 20 years ago. And it would not be the same world 20 years from now. That realization, perhaps more than any specific engineering failure or funding shortfall, defined the stakes of everything that was still to come. Because the question was no longer simply whether the barriers to exploration could eventually be overcome. It was whether they could be overcome before the thing being explored was transformed into something different from what made it worth exploring in the first place. The programs that emerged from this more mature understanding of the problem were not identical to one another, and that diversity was itself a form of intelligence. Different research groups, operating under different constraints and with different areas of expertise, pursued different points of entry into the same fundamental challenge. Some focused on the descent problem, refining hot water drill systems to operate faster and cleaner than any previous design. Others concentrated on the vehicle problem, building and testing autonomous platforms in accessible under-ice environments. Still others worked on the data problem, developing algorithms that could extract the maximum useful information from the limited communication channels that physics permitted through thick ice. None of these efforts was sufficient on its own. Together, they constituted something that resembled a coordinated approach even when the coordination was imperfect. One of the clearest demonstrations of what this matured approach could achieve came not from the Arctic directly, but from the margins of the Antarctic ice sheet, where researchers began deploying autonomous underwater vehicles beneath ice shelves with a consistency and ambition that previous programs had not managed. These missions revealed, in more detail than any previous observation had captured, the geometry of the ice-ocean interface in the regions most vulnerable to warm water intrusion. The underside of floating ice shelves, which had been almost entirely unmapped, turned out to be sculpted into complex terrains of channels, ridges, and melt pockets that controlled how warm water circulated beneath the ice and how efficiently it transferred heat to the ice above. That sculpting was not random. It was produced by the same melt process it influenced, a feedback loop that shaped the geometry of the interface and through it the rate of melting. The significance of these findings for the Arctic was not hypothetical. The same physical processes, warm ocean water reaching the underside of floating ice, creating melt patterns that fed back into the circulation of the water itself, were operating beneath Arctic glaciers that terminated in fjords. Jakobshavn Glacier in western Greenland, one of the fastest flowing and most extensively studied outlet glaciers in the world, had been losing mass partly through precisely this mechanism. Warm Atlantic origin water had been intruding further into Ilulissat Fjord than it had during the preceding decades, reaching the glacier's calving front and melting its base, thinning it and destabilizing it in ways that drove the acceleration and retreat documented in the satellite record. Understanding what was happening at the ice-ocean interface of Wakopshavn required the same kind of under-ice vesicle surveys that the Antarctic programs were beginning to deliver. The technology was no longer speculative. It was producing results. The question was whether it could be adapted quickly enough to the specific geometries and conditions of the Arctic fjord environment to be useful before those environments changed further. That adaptation was underway, and it was producing insights that complicated the simple narrative of barrier and delay that had characterized the field for so long. Because as the vehicle programs pushed further into accessible subglacial and sub-ice shelf environments, they kept encountering things that the models had not predicted and that the remote sensing record had not resolved. The ice-ocean interface was more varied than expected. The patterns of warm water intrusion were more sensitive to fjord geometry than the large-scale ocean circulation models suggested. Small-scale features of the seafloor, ridges and sills that were below the resolution of existing bathymetric surveys were controlling where warm water could reach and where it could not, in ways that made a critical difference to the melt rate, but that had been invisible to the instruments doing the observing. This persistent pattern of approaching a system with what seemed like adequate observational capability and finding that the system's most consequential features operated at scales below that capability was one of the recurring themes of the entire effort to understand what happened beneath polar ice. Every time the resolution of observation improved, it revealed processes occurring at smaller scales that were nonetheless controlling outcomes at much larger ones. The connection between that small-scale structure and the large-scale behavior of ice sheets was not a technical nuisance. It was the central scientific problem, and it was a problem that could only be addressed by getting instruments close enough to the relevant interfaces to observe them directly, which meant going beneath the ice. The programs developing borehole access systems for the deep subglacial environment were by this point operating with a clarity of purpose that earlier generations had sometimes lacked. The revised designs incorporated lessons from every previous attempt and every analog study. The sterilization protocols were more rigorous, validated against the revised contamination standards developed in dialogue with the planetary protection community. The borehole maintenance systems were more energy efficient, designed to minimize the fuel that had to be transported to remote field sites. The vehicle concepts were smaller and more maneuverable, shaped by what the analog work had revealed about the spatial structure of subglacial environments. And the data architecture was more realistic, built around what acoustic and fiber optic communication could actually deliver rather than what the science ideally wanted to receive. What these programs had not yet achieved was deployment to the deep Greenland targets that represented the most scientifically valuable and most logistically demanding objectives. The preparation was ongoing. The baseline characterization surveys were accumulating additional seasons of data. The instrument systems were being tested in accessible proxy environments and returning from each test with a revised list of what needed to change before the next one. Progress was real, but it was incremental, and the gap between current capability and required capability, while narrower than it had been, had not yet closed. And here, at the point where the honest account of the effort reaches its present condition, is where the last surprising detail belongs. Because it comes not from the deep interior of the Greenland ice sheet, where the oldest and most isolated subglacial environments are located, and where direct access remains the most distant prospect, but from the margins. From the places where glaciers meet fjords, where ice transitions from grounded to floating, where the subglacial drainage system discharges its contents into the sea. From the outflow. Researchers who had been analyzing the chemistry and biology of subglacial outflow from multiple Greenland glaciers over an extended period made a finding that required careful handling precisely because its implications were large and its confirmation was still ongoing. They found that the dissolved organic carbon being exported from beneath the Greenland ice sheet was not geologically old in the way that most subglacial organic material was expected to be. Ancient ecosystems, isolated for tens of thousands of years, should be metabolizing carbon that has been cycling through the subglacial system for a very long time, carbon that carries the isotopic signature of great age. What the outflow samples from several Greenland glaciers showed was a mixture. From some of the dissolved organic carbon did bear the signature of ancient cycling, but a portion of it appeared to be relatively young, geologically speaking, bearing an isotopic signature more consistent with material that had entered the subglacial system recently from the surface. The most straightforward interpretation was that the acceleration of surface melt over recent decades had been delivering significant quantities of surface-derived organic material to the glacier beds through moulins and crevasses, and that this material was being processed by the microbial communities in the subglacial drainage system before being exported to the ocean. That interpretation had consequences that went beyond the biology of the subglacial environment itself. The organic carbon being exported from beneath the ice into the Arctic Ocean was a source of nutrients for marine ecosystems, and the quantity and character of that export was changing as the volume and timing of meltwater delivery to the glacier beds changed. The ocean's biological productivity in the fjords and coastal waters surrounding Greenland was being influenced by processes happening kilometers beneath the ice through a pathway that had barely been characterized a decade earlier, and that was now changing rapidly as the climate drove more surface water into the subglacial system. What made this finding genuinely surprising and genuinely important was not just the mechanism. It was what it implied about the connectivity between the surface world and the subglacial world that researchers had long assumed was a one-way or at most weakly bidirectional system. The standard model had treated the subglacial environment as a sealed archive that was influenced by surface processes through the slow delivery of meltwater, but that was otherwise isolated, its biology and chemistry evolving independently of the surface. The outflow data suggested that the isolation was more permeable than that surface organic material was reaching the bed in quantities sufficient to influence the subglacial community, and that the community's processing of that material was producing an export signal detectable in the coastal ocean. The subglacial world was not simply sealed beneath the ice. It was in active exchange with the surface above it and the ocean around it, through channels that were invisible and largely unmeasured, operating on timescales that varied from days to years depending on the structure of the drainage system and the intensity of surface melt. This connectivity reframed the importance of subglacial access in a way that was different from every previous argument for it. The earlier arguments had been about accessing an isolated archive, about reaching something sealed away and studying it in the state it had been preserved. The new framing was about understanding an active system, a system in which the surface, the subglacial environment, and the coastal ocean were coupled through exchanges of water, carbon, nutrients, and microorganisms that were changing as the climate changed, and that were already influencing ecosystems far beyond the ice itself. Studying that system required access not because the archive needed to be opened, but because the exchange processes could not be characterized from either end alone. Knowing what entered the subglacial environment from the surface and what emerged from it at the margin did not tell you what happened in between. What happened in between was where the transformation occurred, and the transformation was what mattered for everything downstream of it. This was the loop that closed the scientific argument most completely. The question of why we could not truly explore beneath the North Pole's glaciers had always had an implicit second half, and why does it matter that we cannot? The answer to that second half had grown progressively more concrete through the entire arc of this story. It mattered because of what the subglacial environment told us about ice sheet dynamics and sea level. It mattered because of what it preserved about past climates and ancient biology. It mattered because of what it could tell us about the possibility of life in icy environments on other worlds. And now it mattered because the subglacial environment was not a passive archive but an active participant in the Earth's carbon cycle and the Arctic's marine ecosystem, a participant whose behavior was being altered by the same warming that made understanding it so urgent, and whose influence on the ocean and the climate extended far beyond the geographic boundaries of the ice itself. The barriers to exploration beneath the North Pole's glaciers had not fallen. Every one of them remained real. The pressure still crushed equipment. The ice still refroze around bore holes. the darkness still defeated the sensors that depended on light. The communication channels were still inadequate for the data rates the science required. The contamination risks still constrained what could be introduced into environments that had been sealed for geological timescales. And the target itself was still changing faster than the programs designed to study it could follow. But the understanding of why those barriers mattered had deepened beyond anything that could have been articulated when the first radar surveys hinted at liquid water beneath kilometers of polar ice. The hidden world was not simply hidden, it was consequential, connected, and actively changing in ways that propagated through the climate system and the biosphere and the planetary record of life's persistence in extreme environments. Understanding it was not a luxury of scientific curiosity, though it was that too. It was a functional requirement for understanding what was happening to the Arctic, to the ocean, to the climate, and to the question of where else in the universe conditions like these might exist and what they might be harboring. The programs working toward that understanding continued. They would continue for years and decades beyond any point that could be called a conclusion. The ice would keep moving, the climate would keep warming, the drainage systems would keep reorganizing. The communities of microorganisms evolving in darkness beneath kilometers of pressure would keep metabolizing, dividing, adapting, and dying in rhythms governed entirely by forces that had nothing to do with what was happening on the surface above them. And somewhere in the spaces between those rhythms, in the chemistry of water that had not touched air since before the last ice age ended, in the sediment layers that recorded the waxing and waning of ice sheets over millions of years, in the genetic sequences of organisms that had been evolving in isolation since before modern humans walked the Earth, the answers to some of the most important questions in climate science and biology and planetary science were waiting, as they had always been waiting, in the cold and the dark and the silence beneath the ice. The gap that separated those answers from the people trying to reach them was not fixed. It was narrowing, haltingly, season by season, system by system, lesson by expensive lesson. Whether it would narrow fast enough, before the environment on the other side of it changed into something that no longer held the same answers, was the question that no one could answer with confidence. It was a race without a finish line visible from where the runners stood. And yet the running continued because the alternative, stopping before the answers were found, was something that no one who understood what was at stake was willing to accept. The ice was there, the questions were real. And the effort to bridge the distance between them was among the most important scientific undertakings of the present century, even if its results would arrive slowly, partially, and always in the shadow of how much remained unknown. That is where the effort stands, not resolved, not abandoned. Somewhere in the long, patient, difficult middle distance between the first radar echo that hinted at liquid water deep beneath the polar ice and the day when a machine finally descends into that water and returns with something that changes what we know. The distance is real, the barriers are real. And so is the determination to cross them, one careful season at a time, into the hidden world that the North Pole has been keeping from us for longer than we have existed to wonder about it. There is a particular kind of patience that the Arctic demands of the people who study it. Not the patience of waiting for an answer that is on its way, but the patience of continuing to ask a question that the environment has not yet decided to answer. It is a patience that most human endeavors do not require, because most human endeavors operate in environments that at least nominally cooperate. The bridge gets built, the experiment runs, the data returns, but beneath the polar ice, the environment does not cooperate. It moves when stillness is needed, it seals what was open. It changes the question while the answer is still being assembled. The researchers who have spent careers on this problem understand that patience not as resignation but as a form of disciplined attention, a commitment to remaining present at the edge of something that has not yet given way. What that patience has produced across the decades documented here is not the answer to the central question, but something arguably more durable. It has produced an honest accounting of what the question actually is. The early framing that we simply needed better technology to drill deeper and cleaner turned out to be correct in its particulars but incomplete in its scope. Better technology was necessary, and the technology did improve. But the environment beneath the ice was not a static vault waiting to be opened. It was a living system, dynamic on timescales from days to millions of years, coupled to the surface and the ocean in ways that made every measurement conditional on context and every conclusion contingent on the next season's data. Understanding that fully took time, and the understanding itself changed what kind of access was needed and what would be done with it once it was achieved. That shift, from thinking about subglacial exploration as an engineering problem, with a definable solution to thinking about it as an ongoing relationship with a system that would always be partially beyond reach, is perhaps the most significant intellectual development in polar science of the past half-century. It is a shift that has analogues in other fields where humans have tried to study systems far larger and more complex than themselves: the ocean, the atmosphere, the genome. In each case, the initial expectation that sufficient data would eventually produce complete understanding gave way to the recognition that the system's complexity was not a temporary obstacle to clarity, but a permanent feature of how it worked, one that demanded humility as a methodological stance rather than temporary posture while better tools were being built. The Arctic subglacial world has imposed that same humility, and in doing so, it has made the science more honest and ultimately more powerful than it would have been if the barriers had yielded easily. A science built on the assumption of complete access would have been tempted to overinterpret its early findings, to treat single-point samples as representative, to mistake the accessible margin for the inaccessible interior. The difficulty of access forced a slower, more careful construction of understanding, one that required every inference to be grounded in indirect evidence and every indirect inference to be tested against every other line of evidence available. It is slow science, and it will remain slow. But it is also rigorous in a way that the urgency of the questions demands. The urgency of those questions has not diminished. If anything, it has intensified in ways that connect the hidden world beneath the ice to decisions being made at every level of human society. The rate of ice loss from Greenland and the wider Arctic is a number that appears in insurance actuarial tables, in infrastructure planning documents, in the calculations of coastal communities around the world. The uncertainty in that number traces directly back to the subglacial processes that remain inadequately characterized. Every decade of continued uncertainty is a decade in which decisions about seawalls and drainage systems and port facilities and coastal development are being made with less information than the decisions require. The cost of that uncertainty is not abstract. It is measured in infrastructure that may be built to the wrong specification, in communities that may be inadequately prepared, in resources that may be allocated against a risk profile that the science cannot yet define with sufficient precision. And there is still the biological question, the one that sits at the intersection of the most science and the most speculative. If life persists in the sealed dark water beneath the North Pole's glaciers, it is not there because it chose to be or because it was placed there by any process that had a destination in mind. It is there because life, wherever the right conditions exist and enough time passes, finds a way to occupy them. That is not a metaphor or an inspiration. It is an empirical pattern documented in boiling springs and radioactive waste and Antarctic rock and deep ocean sediment and places we had not thought to look until we looked. If it is true beneath the Arctic ice, as the outflow data increasingly suggests it may be, then it is evidence that habitability is not the rare exception we sometimes imagine it to be, that wherever water and energy and time converge, the probability of biology rises towards something other than negligible. And that changes how we read the solar system and the galaxy, and the question of whether the universe is a place where life is common or a place where our existence is a profound anomaly. That question will not be answered from beneath the North Pole's glaciers alone. But the answer will be shaped by what is found there or not found there. The presence of life would argue for abundance. The carefully confirmed absence of life after genuine access was achieved and contamination was accounted for would argue for constraint for conditions more specific than the current theory of habitability requires. Either answer advances the science, neither answer is available yet. What is available is this. A world beneath the ice that is real, that has been confirmed to exist by every indirect means available, that is changing in response to forces that are themselves the product of decisions being made at the surface, and that holds within it information that connects the deep past of this planet to its near future, and to the question of life's prevalence beyond it. A barrier that has been characterized, honestly and in detail, as a system of interconnected physical and biological and institutional constraints that resist simple solutions and demand sustained, coordinated, patient effort and a community of researchers who have not stopped trying, who take the difficulty of the problem not as a reason to step back but as a measure of how much the answer matters. The ice above that hidden world is thinner than it was when the first radar echoes hinted at what lay beneath. The drainage systems beneath it are more active. The outflow chemistries is changing. The window for studying these environments in anything close to their current state is real, and it is not unlimited. What happens in the years ahead, in the programs being developed, and the field campaigns being planned, and the instruments being tested in accessible proxy environments around the world, will determine how much of that window is used, and how much is allowed to close before the tools that could use it are ready. That is the story as it stands, incomplete because the environment it describes is still changing, unresolved because the questions it raises are still open. And genuinely important in a way that connects the cold and the dark beneath the Arctic ice to the world that the rest of us inhabit above it, in ways that are still being mapped and still being understood. If this kind of patient, honest exploration of Earth's hidden places is something that keeps you curious, if you find yourself drawn to the questions that sit at the edge of what we know, then this is the place for you. Subscribing keeps these journeys coming, and it helps this channel find the people who are looking for exactly this kind of quiet, careful wonder. Thank you for spending this time in the dark with us. There is more down here worth exploring, and we are only just beginning to find our way.